Hello everybody, welcome back to Alex Does LeetCode, where we do programming problems on stream live. Now, unfortunately, I just found out that I spent the last hour streaming. I thought I was live, but I wasn't because I didn't press the go live button on YouTube Live. I had my mic set up and everything. I was talking and I was going through our usual stuff, but I was not live. Let me just make sure that I am live right now, because I still don't see myself. Interesting. Give me a few seconds. Okay. Your videos. I still don't see myself. Okay, now I think I do. Okay, I think I do see myself now. Okay. Let's do a quick chat test. Sorry guys, I greatly apologize for this. I greatly apologize, by the way, for if any of you guys were waiting before to get in the channel and you were wondering why there was a message. There was a message that says that the stream has not started. Well, that's a fake message. That's a fake message. I actually started, but YouTube was not cooperative, and it turns out I was talking in the air for about an hour. But you know, it's okay. Now we're back on live. Now I'm talking to you, and now you're here, and now we are ready to tackle some programming problems together. But before that, I want to give a quick survey, alright, to anybody who's watching this channel, either now, if you're watching afterwards. Make sure you type in the comments. I want to know a little bit about what you guys think about the time and day of week. Does this work for you? Because I realize that my audience is very global. There are people, I'm based in the United States. Many of you guys are based somewhere else in the world. So let me know if this is a good time for you, or if you prefer to do this some of the time, all day. I'm flexible. Also, let me know if this is the level of difficulty that's alright, or should I go back down to an easier set of problems. I'm flexible on all these things. At the end of the day, I just want to make sure that we all go on this journey of learning together. So whatever is most effective for you guys works for me. Now, let's get back. Now, with that out of the way, let's get back into it. Finally, we are good to go. Okay, I see that my screen is actually changing, so this makes me happy. This makes me a little bit more confident that my stream is actually running as it should be. All right, so today we're gonna do something a little bit different, right? Last weekend, I did a programming contest, and many of my viewers did it at the same time as me. So we all did a programming contest together on LeetCode as a channel, and it was a lot of fun. I had a great time to myself. There are 4 questions on the contest. I managed to do 3 of them, and I was stumped on the last one. Some of my viewers, I think, managed to get it, but a lot of people were also stumped on the last one. And they said, people wanted to know what the answer was, and I was stumped. I couldn't give you the answer right away. So I promised that I'll make another video. Talking about question 4 from last week's programming contest. If you missed last week's programming contest, feel free to jump back there and watch it. I think it was a surprisingly popular video. People apparently like it. So go check it out, and maybe you can learn something from doing this contest together with me. No, more importantly though, I was not able to do this, so today is sort of my apology, like the makeup lecture for the answers from the last time around. Okay, so let's start by talking about the problem. So this is the problem in question. This is question 4 of last week's contest. I will probably be doing more programming contests in the future. If that's something that's content that you enjoy, make sure you get in the comments. And let me know. And as usual, like and subscribe. That helps me a lot. It helps me a lot for the YouTube algorithm. Okay, so the problem looks like this. There is a company with N branches across the country. Think of like McDonald's or something, or Starbucks. There's a bunch of McDonald's across the country. Some of them are connected by roads. Initially, all branches are reachable from each other by traveling some roads. The company realized that they had to cut spending, very McDonald's-like. They decided to close down some of these branches. However, they want to ensure that the remaining branches have a distance of at most max distance from each other. They will close down some branches and still have at most max distance from each other by traveling along the roads. The distance between two branches is the minimum total travel length to reach one branch from another. This is actually a pretty confusing way to describe it. Once you see the picture, I hope it'll be easier. Okay, you're given to an integer n max distance and the list of roads, and now you have to return the number of possible sets of closing branches, so that each branch has a distance of at most max distance from any other branch. Let me just double check. Okay. I'm suspecting my Let me just double check. Okay. Okay, cool. Now my sound is good. Oh man. It was a real harrowing experience to stream for 1 hour and then realize that hey, nobody can see me because I didn't hit the go live button, so I actually was not live. Alright, so let's look at one of these examples. Okay, so this is essentially a graph problem. Some of you guys, I don't know what your sort of level of computer science experience might be, but if you understand, if you've taken some basic introductory courses, you would have heard of graph theory. So this is basically a graph problem. You can turn all these words into a picture that looks something like this. We have 3 branches here, 0, 1, and 2. Okay, these are the roads between them. And you know this based on the input. N is 3, so 0, 1, 2, and 3. Max distance is 5. Roads 0, 1, 2. How do I read this? Well, it says from branch 0 to branch 1, it has a road of length 2. So that's this road right here. Let's change color. So this guy is this guy. And then let's change another color. This guy, 1, 2, 10, 1, 2, 10 is this guy. You see? 10. Okay? So what you get is basically you get the number of different branches. I don't like the word branch a little bit. I'm going to use the graph theory word node, if you guys have heard of it. Just a bit of vocabulary. Or in some formal lingo, they call it a vertex. For our purposes, these are basically, we'll treat them as the same thing. When you hear the word node or you hear the word 0 people watching the stream, I don't know who you're teaching to. Hey, Pranav, how's it going? Yeah, sometimes it is how it is. For small streamers, there aren't a lot of people watching. But thank you for tuning in, though. So welcome, Pranav. Okay, so node vertex, it's going to be the same, all right? I'm going to assume that this is the same thing. Okay, so here's what we have. So the first step is we want to conceptualize the input in this pictorial form. You have these nodes and you have these roads between them. Okay, and let's look at what else it's asking for. Now, this part is a little bit tricky. I was a little bit tripped up by this. So initially, I thought what we want was to figure out what branches to close. But it turns out that what we want is count the possible number of possible sets of closing branches. So it's kind of weird. It's kind of weird thing. And I'm going to go through it one by one. Basically, what it's trying to say is that it's trying to say, if you look at this picture, okay, what branch can I close? So this picture does not agree with the constraint, right? It says max distance is 5. Max distance is 5. This branch number 2 is 10 units away from these two other branches. So it's very far away. So this violates the constraint. So in order to make this agree with the constraint, you want to close branch number 2. And so you might think, okay, the answer to this is close branch number 2, right? If branch number 2 is done, branch 1 and 0, 2 distance apart, they are A-okay. But the thing is, what this question is really asking for is all possible sets of closing branches. So branch number 2 is not the only answer. There is also, you can also close 1 and 2. You close both 1 and 2, you're left with 0, right? If you're left with 0, then 0, it does not violate the constraint. Everybody is maximum 5 distance from each other. There's only one guy. Likewise, you can close 1, you can close 0 and 2. So same thing. You close 0 and 2, there's only one left. And in fact, you can also close 0 and 1. That's also a valid solution. It might come as sort of a counterintuitive solution. So 0 and 1 is a counterintuitive solution. Because, hey, if you close 0 and 1, well, 2 is very far away, right? But if you close both 0 and 1, then, well, there's only one guy left. If he's far away, right? Who cares? He's not far away from anybody else. So this is also a valid solution. In fact, the last solution is you can close 1, 2, and 3. So you close every single branch. Well, it doesn't violate the rule, right? Max distance is 5. Well, there's no branch. None of your shops are open. Then it doesn't violate the constraint of having a max distance of 5. Yep. So the answer here will be 2, 1, 2, 0, 2, 0, 1, and 0, 1, 2, 3. So the answer is the total number of sets, which is 5, which you can see is what they do here. 2, 0, 1, 1, 2, 0, 2, 1, 2, 3. So this is a little bit, like, to me, it felt a little bit weird way of circuitous or roundabout way of doing things. But, it is what it is. The question is asking what it's asking, okay? I will make one small change, though. To today's lesson, though. The way I'm going to present it, I don't like the idea of counting how many different things you can close. It's a little bit backwards to me. So instead, we're going to count the things that we are opening, right? So each of these sets of things we close correspond to opening something. So closing 2 is the same as, let me choose a different color. So closing 2 is the same as opening 0 and 1. Closing 1, 2, 3 is the same as opening nothing. So it's the empty set. Closing 1, 2, 0, 2, and 0, 1 is the same as opening 0, opening 1, and opening 2. Okay? So we're not going to count how many things we close. The way we're going to approach today's solution is we're going to count how many things we open. Okay? So this is a bit like, I will have to admit that this is like a weird kind of question to wrap your head around, but it is what it is. Now, I want to show you guys. Let's go on to the next example. Next example is the same thing, right? Except now you notice that there's something weird going on here, which is that there's an extra road. This road is 20. Well, if there's 2 roads between 0 and 1, well, obviously you take the cheaper one, you ignore the one that's more expensive. And you call it a day. That's all you have to do. Okay. There is one other example that I want to show you, and we're going to do it in slightly more detail. Okay, I'll show you one more example. So let's say the distance between 0 and 1 is 10, between 0 2 is 1, and 1 and 2 is 1. Okay, so let's think about what's the solution for this. Well, if you look at 0 1 and 2, the whole picture, you might think at first that the distance between 0 and 1 is going to be 10, so 0 1 2 is not a solution. And you think that, well, it turns out that's not correct, because to get from 0 to 1, you can actually take a shortcut via 2. It may be longer, but it's cheaper. So instead of 10, the real weight, the real distance between 0 and 1 is actually 2, because you can take a shortcut via node number 2. So 0 and 1 is actually a solution. What else is a solution? Well, 0 2 is a solution. And then 1 2 is a solution. And then 0 1, the sort of single node configurations are all solutions, just because, and then the empty set is a solution. So the answer to this particular configuration is 1 2 3 4 5 6 7. 7. That is the same. This is basically the same graph as this reconfigured. You can see the answer is 7. Yeah. Okay. So let's make this a little bit more complicated. Welcome to everybody who just joined. If you need context for this, this is a question from last week's programming contests. So feel free to go back and check it out. So, oh, actually, let me make these numbers bigger. Okay. So, let's modify this a bit at 3. Okay, now with 4 nodes, it gets trickier. Now it gets a little bit harder to just like visually eyeball it. So we're going to go solve this one using, we're going to be a little bit more systematic about it. So the first step we're going to do is, again, to list down all the possible combinations of nodes that you can keep, of branches that you can keep open. Remember, we're counting the branches we keep open, not the ones we're closing. So if you keep nothing open, the empty set, all good, right? You can keep 0, 1, 2, 3, right? The singletons. Just 0, just 1, just 2, and just 3. This will work, right? And then 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3. Okay, and then for the tripletons, 0, 1, 2, 0, 0, 1, 3, 0, 2, 3, 1, 2, 3. You can see how this starts to get messy. Okay, it starts to get messy, so we need a strategy, an algorithm for dealing with this. Okay. However, those of you who know a little bit more about mathematics will recognize that this is actually a combinatorial problem. This is basically a combination. This is essentially what we call this a power set, which is a combination of all the things that you can select from a set of things. Okay. Once we have generated all the possible sets, we're gonna look at each one and see which one is okay. So these guys are definitely okay. You know. Nothing is fine. Just one branch is always okay. 0, 1. 0, 1, it turns out is not okay. 0, 1, without this 2 here, okay, without 2, you don't get the shortcut. So 0, 1 has a distance of 100 between them. And in this case, let's say your max distance equals 5. Your max distance is 5. Then 0, 1 is not going to work. What about 0, 2? 0, 2, it turns out, does work. 0, 3, nope, doesn't work because without 2, again, there's no path between 0 and 3. There's no path. So 1, 2 works, 1, 3 does not work, and 2, 3 works. 0, 1, 2, 0, 1, 2, yes, works. Notice how 0, 1, 2 works even though 0, 1 doesn't work? Because 0, 1, 2 has the 2, so it allows you to take the shortcut. So 0, 1, 3 does not work. So basically everybody without 2 doesn't work. So the total here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the answer here is 12. Okay? So I hope that this is a sufficient explanation of the problem and what we're supposed to do. And now we're going to go back to putting this into code. So I was trying to, it turns out that this is not this is actually not easy. So and the programming contest itself, I was actually stumped. For those of you who are here watching live, I spent about 45 minutes watching this. I spent about 45 minutes watching this. I spent about 45 minutes on this problem, and I didn't actually come up with a solution for it. And I was a little frustrated by this. And for those of you who have been following my channel for a while, you realize you notice one thing, which is I'm very open about failing to do something. I'm very open with not being successful about something, and that's totally fine, right? If you are failing, right? If you're failing, then you're doing something right because you are learning, you're growing. And even if you don't learn something from a failure, it still tells you you're tackling problems at the right level. So never be afraid to fail. Always be okay with failure. Failure is what it is. It is a part of life. Okay? Just like how there was a comment. Yeah. So failure is just a part of life. Okay? So after I failed to do this problem live, I went back, I thought about it a little while, and I found out that I came up with not just one, but 2 possible solutions. So something good came out of the failure, right? Something good came out of it, which is I thought about 2 possible solutions to the problem. And today, I'm going to introduce you to both of these solutions. I'm going to go through both of them, and we're going to talk about it. And maybe learn something from the whole exercise. The first solution is what I'm going to call brute force. The second solution is called, I'm going to call it dynamic programming solution. Okay, so the brute force solution is easy to write, but it's also slow. And I'm going to show you empirically, experimentally, and as well as mathematically why I say it's slow. How is it slow? Okay, and the dynamic programming problem is harder to write. But it's faster. It's still not fast because this is actually a very slow problem. But I believe the dynamic programming approach is going to get you as fast as you can. Okay, so I went back after the contest to look at what other people do, what other people did, and I realized that the vast majority of the successful participants were actually using the brute force solution. If you are doing a programming contest, you want something that's easy to write. You're graded on how fast you come out with something, right? You don't care if your code actually runs quickly or not. It runs quickly, great. If not, you come with something quickly, it works, right? Who cares? You call it a day. But if you are writing actual code that you want to use in a production system, you want it to be good. So if you're writing real code, you want to use a better, less brute forcey kind of approach. And more importantly, perhaps more pertinently to many of you on the stream, for those of you who are interviewing for technical jobs, you're going to a tech interview, I'm sure you've heard the term dynamic programming before, Okay? So I'm not going to pass up a chance to learn and also to teach about dynamic programming. Just the exercise of writing the solution out using this strategy, using this, I would say, very common strategy, advanced technique, is going to help you practice your dynamic programming skills. So this is what you want to do if you want to write real code or if you want to practice for your interviews. Okay? So with that out of the way, let's first dive into the brute force solution. Well, what does the brute force solution look like? It turns out that brute force solution is pretty much what we've did so far already, right? So look at what we did so far. The first step of what we did is we generated all the possible combinations. All the groups of nodes, all the combinations, the sets of nodes that we can have. And then step 2 is we look at each one and we decide for each group, each combination, is this valid or not valid? We decide that by basically looking at the shortest path between every single node and make sure that no two nodes are more than X distance apart. Now, this is going to involve a power set. There are two parts to this. And then this, for calculating the minimum distance between them, we're going to use the Floyd-Warsaw algorithm. So interestingly enough, I actually didn't know about Floyd-Warsaw. I was going to use some kind of modified Dijkstra's algorithm. Dijkstra's algorithm. This is really famous. If you've taken a college computer science class, I'm sure you've known about Dijkstra's algorithm. That was what I was going to use. It turns out that this is not the best way of doing it. One of my viewers during the contest pointed out that you can actually use Floyd-Warsaw, which is better for calculating the distance between all sets of nodes. Dijkstra calculates from one source node to everybody else. And okay. So the pseudocode is going to look like this. First, generate the power set. And so this will give us a long list, which is like empty let 1, 2, 1, 3, 2, 3, ... So this is what what the power set is. And then for combo, this combination in all combos, I'm gonna calculate the shortest path between them and then check if combo is valid. Okay? So calculating the shortest path between them, we're gonna use and calculating the combo is valid. This is very simple. For I in combo, for j in combo, if distance I j larger than max, then invalid. And then if valid, cal plus equals 1. So if the combination is valid, we increase it by 1. Okay. Now, one thing that is important to note is that in this calculation of shortest path, it has to be done for each combination. This is kind of weird. This is a kind of a weird thing. For each combination, you have to separately calculate the shortest path. Because imagine you've calculated the shortest path for 0 and 1. Now you want to add 2 to it, right? 2 actually affects the distance between 0 and 1. So you have to recalculate each time. So before I continue to show you the code, I am going to go over one more thing, which is the idea of an adjacency matrix. So again, if you have taken a class in computer science, this should be something that is familiar to you. You would have seen a adjacency matrix before. But I want to go over this on my channel because this is an educational channel. And I hope this can teach you a little bit about computer science. Okay, adjacency matrix is basically a n by n matrix that tells us the distance between any 2 points. Instead of having this graph, storing this graph in memory as a list of roads, we're going to store the distance between them. So this is called an adjacency matrix. So distance between 0 and itself is 0. Between 0 and 1 is going to be 100. 0 and 2 is 10, according to this graph I have here. 2 and 3 is 1. This is 100. This is 0. 1 and 2 is 10. And for this, because there's no road between 1 and 3, I'm going to keep it as x for now. Notice I'm not doing the sort of shortest path first. I'm just calculating. I'm just listing down the roads first. We can use this for the shortest path later. Hey, welcome, Baitik. Baitik. Sorry if I get your name wrong. This language is not C++. This is actually Python. So normally I code in Python. I find that it's easier to learn in Python, actually, because C++ has a lot of other bells and whistles. Assuming, if you are expert in C++, you would probably know that. It's got a lot of bells and whistles that I don't enjoy teaching to my students. Okay, so once we have an adjacency matrix, so this is basically the distances. This matrix you can store it as a 2x2 list in Python. In C or C++, you have a 2x2 array. Is basically a two-dimensional array is basically the same thing. This encapsulates all the information about graph that you need. Okay, so with this, what we do is at every step we pick a subset. So for instance, I say, okay, back to here. So if I want to pick, let's say 0 and 1, right? So I want to pick 0 and 1. I want to test if 0 and 1 is a valid combination. I will go to my adjacency matrix. I will pick only 0 and 1. Let me just give it a highlight. And then I will rework everything in my adjacency matrix, recalculate everything in my adjacency matrix to get the shortest path between everything between 0 and 1. So it's done. It basically doesn't change anything. And then maybe later on, what I want to do is I will want to pick 0, 1, and 2. So same thing, I'm going to go back to my adjacency matrix. This time I'm going to have 0, 1, and 2. I'm going to recalculate everything here. It turns out that adding 2 makes traveling from 0 to 1 faster. Adding 2 makes traveling from 0 to 1 faster. Because you can take a shortcut to 2. So if you do that, then you recalculate and you find that this one actually doesn't violate the constraint. Okay, let's say is max distance equals 50. This one doesn't violate the constraint. So 0 and 1, not by itself, not okay, but 0, 1, and 2 combined, that's okay. Right? This is kind of like a this is basically the reason why we have to recalculate. We have to recalculate the shortest path between all nodes and each step. This is why we have to do this recalculation inside of the for loop. We can't calculate the shortest path outside the for loop one time and call it a day. Hi Piyush, welcome back. Welcome back. Always happy to see you again on the channel. I know you were here during the programming contest. I hope that this lesson is particularly helpful to you. Okay, so this is where I take you to the code that I've written. Okay, so all the code that I'm going to show you today, as well as the slides that I've been presenting from, will be uploaded on GitHub. I'm going to upload all of these things on GitHub at the end of today, so you guys can download them from the YouTube video link, and you know, play around with it yourself. Okay, so this is how we actually turn the description that we have, the pseudocode we have, into code, right? And this is Python. And the main function to focus your attention on is this one. Okay, number of sets, self, and max distance roads. The first step, transform everything into adjacency matrix. If there are multiple roads between two things, then take the shortest one. If you're going from I to itself, then is the answer is the distance is automatically 0. Okay, next we're going to have a power set. We're going to create a power set, and we say for S in power set. The way we create a power set is a little bit like, it's funky. This is how we create a power set. So normally, if you've taken a basic CS 101 class, the way your professor teach you to create a power set probably looks like this, right? Power set, if length, it's going to be like recursive. If length of S equals to 0, return, else, return power sets S. And this for the folks who are from C++, this means hold on, let me adjust my video setting. The video has not been kind to me today. Somehow YouTube is just messing up. Let me adjust my video setting. The video has not been kind to me today. Somehow YouTube. Yep. Okay. Maybe some of you are hearing echo. I hope that is a minimum distraction. Okay. So you want to do like a power set plus, and this is very funky notation. You're basically saying power set of S equals to power set minus the first thing in S plus you add the first thing in S to everything in the power set. Okay, so this basically means let me draw it out. The power set of 1, 2, 3 is equals to the power set of 2, 3 plus the power set of 2, 3 with 1 added in front. So basically this is everybody that doesn't have 1 and everybody who does have 1. Okay, so the way I chose to do this in Python is a little bit different. I use something that is very idiomatic in Python. So Python has thank you Piyush for letting me know. I really appreciate that. So Python has a lot of like funky tools. One of them is iter tools that allows you to use very cool functions. I will make a video about this at a separate point. Combinations basically tells you all the combinations from S of size R. So combinations S0 will be the empty set. Combination S2 will be 0, 1, 1, 2, 0, 2, 0, 3, 1, 3, etc. Right? So because we want the power set, we want all the combinations from range r from range 0 until s plus 1. And then we use this function called chain to combine all these combinations together. So this is a little bit more advanced. I do want to make a video about this in the future. So iter_tools is, to me, one of the, this iter_tools library is one of the defining like unique things about Python that makes Python a little bit more fun and easy to program in. Okay, so this generates the power set for you. And once you've gotten the power set, coming back to the main algorithm, once you've gotten the power set, the next step is to update the matrix. So remember the matrix we have, right? If we decide that we want 1 and 2, we decide if we want 1, 2, and 3, then we can't just look at 1, 2, and 3. We have to update 1, 2, and 3 to reflect the shortest path between them. Okay, we have to update this matrix to reflect the shortest path between, and we include number 3. We have to change all this, to the shortest path. Now it's infinity because there's no distance between 1 and 3. But once we, if we pick a subset that includes 3 and 2, then this might go to 11, for instance. Okay, so we calculate the shortest path between them, and then the next step is we check if it's valid. So the isValid function is the same as I described for I invertis, j invertis. If the distance between them is the greater maximum, return false, else true. Blah blah blah. If it is valid, we add count equals count plus 1. Okay, and that's it. That's it for the brute force solution. And to prove to you guys that this actually works, I don't know why I'm going to do that. I will never lie to my audience. I will never lie to all of you. This is the same thing. I just copy and paste the code that I have exactly as I wrote it. And you can see that this is accepted. Okay, so this brute force solution works. Okay, this brute force solution works. Okay, so this brute force solution kind of works. But the thing is, as I was writing this, I got a little bit annoyed because I feel like it's slow. What do I mean by slow? Okay, let's do some big O analysis on this. For those of you who are familiar with big O notation, let's first look at the power set. What is the time complexity of this power set? Well, the size of the power set itself is 2 to the n. So at the minimum, it's going to take 2 to the power of n steps to generate this power set. It makes sense, right? If you know from basic mathematics in combinatorics, if you have 10 things, well, how many different combinations of there are 10 things? Well, 2 to the power of 10, which is 1000. If n is very large, this number becomes very large. And then let's look at what's the complexity of Floyd-Warsaw. Floyd-Warsaw is actually the fastest way to generate the shortest path between all vertices. This is, is a classic algorithm. It's well known, it's proven that this is already the fastest way. This takes O n cube, right? Because it's 3 nested loops, as you can see here. So what does that mean? That means that when I scroll down here, my algorithm here, right? Because I'm calling an on cube function inside O 2 to the power of n, my algorithm, this brute force algorithm, is O 2 to the n times on cube. Oh my god, this is slow! 2 to the power n is super slow, and n cube is super slow, and then you multiply them together. Oh crap, this is going to be very slow. In fact, I can prove it to you empirically by running, let's say, Python It took 576 milliseconds. I ran a few test cases. This is my largest test case. This is actually not that large, right? This is not that large because there's only like 1, 2, 3, maybe about 10, 15 different roads. I have 10 nodes. I can have up to 100 nodes, 100 roads. I only have 15 roads here, right? So this is considered not a big problem, but already it's taking 170,000 steps. I'm gonna, when I upload to this GitHub, you can look at the details of how I calculate these steps. And it took half a second. So this is, hey, Tam Hyung Ha. Sorry, I probably butcher your name. One of these days you got to teach me how to pronounce your name. Welcome. Yes, I'm redoing the problem from the last bi-weekly contest. This is question 4. I got it wrong, but I will say that I found 2 solutions for this, which I thought was really interesting. One is the brute force, which I'm just describing. I'm showing what's the time complexity of the brute force, which turns out is not very fast at all. It's actually pretty slow, right? Its time complexity is O n 2 to the power n times n cube. Okay? So when I was thinking about this, I was wondering to myself, is there a better way to write this? It turns out that maybe there's a way to exploit the inefficiencies in the brute force algorithm. And I'm going to describe to you how we're going to do this. Okay? This is a bit more interesting. So I'm actually very proud of this dynamic. I'm proud and not proud. I'll explain later why. But I'm sort of proud and not proud of the dynamic programming solution. Because I looked at the top solutions from the LeetCode contest, and none of the winners actually got this. Everybody used the brute force solution, which is great, which is what you should do in a contest where you have to write fast, but it's also very slow. So I'm going to see if there's a way to make this a little bit faster. So this is actually not a perfect solution, and I'm actually curious because there are so many smart people watching this. I'm curious if any of you guys can find an even better solution than me. Okay, here's what I'm thinking. Okay, imagine you are, for instance, looking at zero, 1. Okay, you're looking at 0, 1, and you want to calculate the shortest path for 0, 1 using Floyd-Warshall. And this is going to be an ON cube operation, and you calculate for 0, 1. Okay, at some point down the road, you're going to repeat the same freaking thing for 0, 1, 2. You have the same board. Okay. You calculate 0, 1, 2 and 2. Right? And you have to do this. We went over the reason already. You have to do this. You have to do this because adding 2 changes the distance between 0 and 1. So you have to recalculate everything again. Okay? But I'm thinking, well, sure, I can't just add 2 and do nothing else. But is there a way to recalculate, but do it quickly? Right? Is there a way to recalculate this? Not just add 2, but also recalculate the things here, but only for nodes that are affected by 2. So here's what I'm thinking. Okay? So this actually saves quite a bit of time because the shortest path is ON cube. If I can save this, and my sort of hypothesis is that when I know the shortest path for a set, and I add one more thing to the set, and I calculate the shortest path just for that one more thing, I'm going to get ON square instead of ON cube. That's my hypothesis. Okay? And that includes updating all the things inside here to reflect the sort of shortcuts that you can take with this new node. Okay, so you can imagine that this actually extends everywhere else. Well, if you have another board, 0, 1, 3, well, you can use the same shortcut, right? You have this red square that you have already calculated. Well, it's almost the same. It's not exactly the same. It's almost the same. You just have to update a few things inside here to make them the same, right? And then if you think about, right, even more boards down, this might potentially save you a lot of time. Yeah, this might potentially save you a lot of time. Anshuman, welcome. Hello. Welcome to the channel. Okay, so this is the step one. This is the first thing I'm thinking of. First thing I'm thinking of is that I'm going to calculate shortest path incrementally to save time. Instead of calculating from scratch each time, I'm going to calculate them. The second thing I'm thinking of, right, is that let's say 0, 1 is bad. If 0, 1 doesn't work, okay, if 0, 1 doesn't work, well, it doesn't mean that everything else doesn't work. Like everything down the line from here, adding more things doesn't work. It doesn't mean that. We have seen before, adding 2 to 0, 1 actually makes 0, 1 work because you have this like shortcut, right? Let me use red. So 0, 1 doesn't work. I'll use yellow. So 0, 1 doesn't work, but 0, 1, 2, 3, 0, 1, 2 works, right? 0, 1 doesn't work, but 0, 1, 2 works because adding 2 gives you a shortcut, right? So we've seen that, you know, if 0, 1 doesn't work, it doesn't mean that none of these work. But here's the thing though, if 0, 1 doesn't work and if none of these guys work, maybe it means that all these guys will also not work. So that's my hypothesis. That's hypothesis number 2. If a set doesn't work and adding something to the set doesn't make it work, like adding one more thing, I cannot find even one more node to add to the set to make it work, then maybe adding even more stuff will never make it work. That's my hypothesis. So that's my assumption. It turns out that this assumption is actually very shaky. I don't think it's actually correct. But we are going to go through and see what we end up. Okay, so the second sort of way to save time is we call this like early termination, to stop exploring failed paths, failed subtrees. So one thing that's implicit that I didn't actually make clear is that I'm thinking of these boards as a tree, right? As a sort of tree structure. So specifically, let me just erase this thing here first. So hard. Tiny eraser. Okay. One thing I sort of implicitly did, and I'm going to make it explicit here, is I'm thinking of this as a tree structure. I'm thinking of an empty set at the top. At the first level, I add one thing to the empty set. So it's 0, 1, and 2. Those are my first level. In each level, I add more things. So we have 0, 1, and 0, 2. And then likewise 1, 2, 0, and 2, 1. Okay, so each each level, I sort of expand more and more. Now, the thing is, these things are not unique. These branches actually merge back. Like 0, 1, goes to 0, 2, 0, 2 goes to 0, 2, 1. And 0, 2, 1 can also be reached from here. This also goes to 0, 2, 1. So they merge back. It's like a diamond shape. If you actually expand it out and then merge back, it's a diamond shape. And you can see an example of this diamond shape right here. So 0 is here. Your 0, 1, 2, 3 here. 0, 1, and you can think of like let's pick a different color. At the risk of making this very complicated, right? 0, 1 goes to here, and goes to here, and goes to here. Right? And then 3 will goes to here, and then maybe goes to here. So they're a little bit interconnected and they merge back. Now, okay, so that's sort of my brainstorm, right? So the thing about programming is that one thing I hate to do is like people just start writing code. I hate that, right? Don't mark the code first. Just write on paper what your plan is. Come up with the plan first and then you execute it. Just don't rush in blindly, okay? So let's say I come up with a plan that looks something like this. So it looks like I have a plan here, which is instead of generating the whole power set, I'm going to explore the space by adding one new thing at each time. So from 0, I add one new thing, I get, from empty, I get to 0. From 0, I add one thing, I can add 1 or I can add 2. Let's say I get to 0, 2. 0 and 2. And at 0 and 2, I add one more thing to get to 0, 2, and 1. And so on and so forth. Right, so the idea here is at every step, I add one thing. I just add one more thing. And I'm going to make use of this property, this hypothesis, that adding one thing allows me to update the matrix cheaply. Instead of O(n) cubed, I only need O(n) squared. Okay? So that's the idea behind it. Let's go to the code. And this is what the code actually looks like. So this is solution 2 for LeetCode contests. As usual, all these things will be uploaded to GitHub after today's live stream. I'm going to upload my slides to GitHub also. So feel free to download them and try it out for yourself. Okay? So the way I did this, there's a valid function. Let's go to the main function and look at it. So the main function looks like this. Step 1, you turn rows into adjacency matrix. We've done that before. And then step 2, we call this helper recursive function. The reason is, normally when you deal with trees, you will want some kind of recursive function. So recursive function is helper. So helper is not very long, but it's actually like this thing took me almost a day to write. Which is shocking because it's like 20 lines of code. So the way this works is basically I keep two lists. I keep a use and a no use. Use is the nodes that I'm going to use, that I'm using, which corresponds to like this yellow part here. Use is in yellow. Okay, no use means that I will not use these things in the subsequent exploration of this subtree. When I calculate my adjacency matrix, when I update my matrix, I only care about use. No use is there for exploration purposes only. So at each step, if everything is either used or unused, then basically I've come up with a sort of set, right? I reached the sort of leaf node, the bottom of the tree. I've come up with a set. So if I can reach this place, then yeah, it's 1. Because I'm sort of counting the sets, I don't actually have to write out what it is. If not, then I will look at the number of unallocated nodes. Let me see if I can draw it out to make it a little bit better. Draw it out. Okay, at the beginning, used is empty. And then unused is also empty. So I'm going to do two things. One is I'm going to say 1 for use. and then unused is still empty. Then the other one is I would not use 1. Okay, at every step, the way I do my exploration looks like this. I either use 1 or I don't use 1. So at every step, I pick a node. I pick an unallocated node, something that is not in use or unused, is not assigned yet. And then I want to pick a node that is legal. It's legal. So for instance, if I have my previous one, right? 0, 1, 2, 3. I pick 1. That's not legal, so I want to pick 2. Okay, I don't want to pick 3 because 3 is not legal. You sort of get into a bind right away. So I'm doing something here to make sure I only add legal nodes. So if I can find a legal node, if I can find a node that keeps this valid, remember the assumption here, which is I don't want to explore branches where I don't want to explore subtrees, right? I don't want to explore subtrees where all of their parents are invalid. If all of your parents are invalid, I don't want to explore you. I'm going to assume that you're also invalid. And that hopefully will save me a lot of time. Sorry, wrong tab. Yeah, okay. So the next thing is I'm going to check that it's valid. If it's valid, I found a V. V is my next candidate. I'm going to do 2 things. I'm going to explore if I use this, and I explore if I don't use this. What it means is, let's say at the beginning my use is nothing and my unused is nothing. I'm going to say either I use it or I don't use it. And if I use it, I pick my next node, let's say it's 2. I can either use 2 or I can say I don't want to use 2. No matter what, I will never use 2 again in this subtree. So what this unused means, it means that the rest of this subtree will never have 1. Will never have 1 in the used. Never use 1 again. So this guarantees that this subtree and this subtree has no overlap. This guarantees that these two have no overlap. So as I mentioned earlier, because the tree is not a triangle, it's a diamond shape. So at some point they're going to converge back to each other. Yep, they're going to converge back to each other. So I did a memoization. I have vertices memo to keep track of whether I've seen this matrix before. So I don't have to check validity for a lot of different matrices. Okay, so I am going to leave this code up for you guys to explore on your own. But thing I do want to point out is I want to look at the differences in speed. Okay, so this is the previous one. For 1, for 2, I ran the same set of test cases, right? Exactly same set of test cases. For closing branches 2, this is the dynamic programming one. This is the brute force one. The brute force one for test case 6, which is this guy over here, with a whole bunch of 10 nodes and a bunch of like maybe 15 roads. It took the brute force solution 770,000 steps to do it. And later on, you can download the program yourself to look at how I calculate steps. It also took 500 milliseconds, which is quite a while. You can feel it pause visibly for a while before I continue, right? If I use the dynamic programming solution, it only takes 11 milliseconds, which is more than a order of magnitude difference, which is like 50 times faster. And the number of steps it takes is 500 times fewer. It takes a lot fewer steps and it's a lot faster. So this dynamic programming solution works well. However, there's a catch though, which is I do this early termination of the exploration, which means that when I can't find a next, if I can't find a next that will make my my matrix valid, I'm just not going to explore the rest of the subtree. This turns out to be not a correct assumption. I wrote this and then I realized after testing it a bunch of times, it works for like 99.999% of the cases, but there are some cases where you have to add two things at the same time. You know, there are some cases where you have to add both 3 and 4 at the same time for this to work. So my algorithm actually fails on these kind of cases. So the algorithm doesn't work that well, which is unfortunate. I might think about this a little bit more in the future to see if I can fix this. This looks like a pretty critical bug. I don't know how easy it is to fix, but I have to work on it in the future, right? But in terms of speed, it's actually pretty good. As you can see here, you know, this is how you calculate a modified version of the Floyd-Warsaw algorithm. You notice there's 2 for loops instead of 3. And the reason is because we're only adding one new thing, right? If you're only adding one new thing, that new thing has to participate in all the routes that you're looking at. So you only really need 2 for loops instead of 3. So this is going to be O(n) squared, which makes this an order of magnitude faster. And plus, with like with the trick of not exploring extra branches, it just makes the whole thing a lot faster. Okay, so closing thoughts. It turns out well. I'm happy that I didn't actually get to question 4. Ironically, I'm happy that I had a chance to actually dig deep into question 4 that we looked at the last time. Because this means that we not only find the sort of default brute force solution, we also got a chance to explore a dynamic programming version of the solution, which gives me practice doing dynamic programming. Even though that's not the best way to win a programming contest, look, I don't care about winning programming contests. This channel is about education and I want you guys to learn more about programming. You want to learn more about dynamic programming, trust me, especially if you're doing tech interviews, okay? So that's pretty much it for today's discussion. I hope that this was useful to you. I would love to get feedback from people about, one, does this time zone work for you? Because I know many of you are global. Do you want a different day, or do you want earlier or later in the day? And 2, I am very curious if the level of difficulty is okay, because today's problem is really hard. It's really hard. And when I went through a dynamic programming solution, it makes it even harder. So I'm curious if this is the level of difficulty that you guys are comfortable following on a live stream. If not, we can go back to easy problems on LeetCode, or we can go back to medium problems if you guys want. Spam in the chat, write in the comments, let me know. As usual, please like and subscribe to my channel. Every like helps. Every comment helps. I'd love to know what you think. And thank you for your support. I'm signing off. Take care, folks. Bye-bye. PU, yeah. New dynamic programming. Yep. Maybe medium question. Yep. Thanks you. That is good feedback. I will definitely look into that. Thank you. And I appreciate you, PU, for being a returning viewer. I hope this time works for you. I assume that many of you are from India, because that's what the YouTube analytics is telling me. All right. Take care. Goodbye and see you next time for regular programming.